Have you ever wondered why one app on your phone is just lightning fast, while another one just chugs along, seemingly stuck in mud? Well, behind every single piece of software, there's this kind of hidden language that developers use to predict and describe its speed. Today, we're going to pull back the curtain and learn how to speak it. Okay, so at the very heart of programming, there's this fundamental conflict, right? It's a choice that developers have to make every single day. Should I write code that's simple and easy for anyone to understand? Or should I write code that's crazy fast and super efficient? And believe me, this is not just some academic question, it's a real-world dilemma with huge consequences. Now you might be thinking, hey, why not just run the code and time it with a stopwatch? And that's a good thought, but here's the catch. A program that zips by in 1 second on a brand new supercomputer might take 10 agonizing minutes on your old laptop. See the problem? We need a universal way to measure efficiency, one that doesn't care what kind of hardware it's running on. And that brings us right to the core of it, the programmer's dilemma. Developers are constantly in this tug of war, trying to serve two masters and balance two goals that are often pulling in completely opposite directions. Let's break down exactly what those are. So on one hand, you want code that's just simple, clean, code that another programmer, or even you, 6 months from now, can look at and immediately get what's going on. But often, the simplest way isn't the fastest. On the other hand, you might need code that is just brutally efficient, squeezing every last drop of performance out of a machine, even if it ends up being way more complex. And this choice can mean the difference between an operation taking a few seconds or a few years. No joke. So, how do we solve this? How can we actually talk about an algorithm's speed in a way that's consistent, no matter the computer? Well, computer scientists came up with a special mathematical language to do exactly that. It's a tool that lets us compare how algorithms behave as they get more and more work to do. This language has a kind of fancy name, asymptotic notation. But don't let the name scare you. The core idea is actually really simple. We don't care about the exact running time in seconds. What we care about is how that running time changes as the amount of data we feed it gets bigger and bigger. Does it stay flat? Does it grow at a nice steady pace? Or does it just explode? That's what really matters. Now, inside this language, there are 3 key words we're going to focus on. There's big O, which is all about the worst case scenario. Then there's big omega, which describes the best case. And finally, big theta, which is the most precise of them all. You can think of them as giving an upper, a lower, and an exact speed limit for our code. Let's start with the most famous one of the bunch, big O. This is the one you'll hear about all the time, and for good reason. It acts like a performance guarantee. It tells you the absolute worst-case performance you can ever expect from your code. The best analogy for big O is a speed limit on a highway. Your algorithm might be much faster than the limit most of the time, and that's great. But big O is a promise. It guarantees that your code's performance will never, ever be slower than that limit. It sets a ceiling, an upper bound that you'll never break through. And this illustrates it perfectly. Check out a function like 100n plus 5. Now, for small numbers, that 100 makes it seem pretty big, right? But now look at n squared. As n gets larger and larger, n squared just grows exponentially faster. It completely leaves 100n plus 5 in the dust. So n squared creates this ceiling that the other function just can never cross. That's why we say it's bounded by n squared, or O of n squared. All right, so we've set the performance ceiling with big O. Now let's do the opposite and establish the floor. This is where big omega comes in. It describes the absolute best-case scenario. So if big O is the speed limit, big omega is like the minimum speed you have to maintain on that same highway. You know those signs, minimum speed 45? It's a guarantee that your algorithm will never perform faster than this bound. It establishes a performance floor, a baseline that you can always count on. Let's look at an example to make this stick. Imagine a function that grows like n cubed. Well, no matter how big your input n gets, n cubed is always going to grow faster than n squared. So because the growth of n cubed is guaranteed to be at least as fast as n squared, we can say that n cubed is big omega of n squared. That n squared is its performance floor. So we have a ceiling with big O, and we have a floor with big omega. But what happens when that ceiling and that floor are basically the same thing? Well, that's when we can use the most precise measurement of all, big theta. My favorite analogy for big theta is just setting your car on cruise control. You're not going faster, you're not going slower, your speed is locked in. When an algorithm's worst-case performance, it's big O, And its best case performance, its big omega, have the same rate of growth. We use big theta to say its performance is tightly bound.
So this is the crucial point. For an algorithm to be described as big theta of n squared, it has to do two things. First, its performance has to be bounded from above by n squared, which means it's O of n squared. And second, it has to be bounded from below by n squared, which means it's also omega of n squared. Its growth is perfectly sandwiched. It's an exact fit.
Okay, I know, that was a lot of theory. So how do programmers actually use this stuff in the real world? Do they sit there drawing graphs for every line of code? No, of course not. It turns out there's a really simple, practical shortcut that everyone uses. And here it is, the big aha moment. In practice, this is all you really need to do. First, you look at all the different parts of your function, and you find the one that grows the fastest. That's what we call the dominant term. So for 3n squared plus 4n plus 1, the 3n squared part is eventually going to dwarf everything else. Then, second step, you just drop any constant numbers multiplying it. So 3n squared just becomes n squared. And that's it. That's your big O. See? Way simpler than it sounds.
So there you have it. You now speak the language of code speed. The next time you're using an app that's loaded with a million cool features but feels a little slow, or maybe another one that's super simple but blazing fast, you'll see the choice the developers made. You'll see those hidden trade-offs. So think about it. What compromises are being made in the technology you use every single day?